Yeah. How'd it go last week? I did. Right. Yeah. I did it last night, so maybe people have been asking about it, but like I'm here, so I'm and it's just great.
That's cool, right?
Yeah, cool.
The projects, is it still? No,
Yeah, I'll do it.
Yeah.
Okay. We should do today. Okay. Let's get started. People will be trickling in. It's definitely the end of the semester. There's like a third of the classes here today. Okay, before we get started, so homework 3 due last week. Looks like most everybody's got it turned in. That's great. This week, proposals for the projects. There's been a lot of questions coming my way to the TM's way. Hopefully, we're answering people's questions, and you're kind of getting clear on that. Any questions right now from those of you who are here, just about mechanics there, or anything at all on the project proposals? Should be really should feel really simple. This is not something meant to be some major research project. This is going after something that seems interesting to you. Usually, you find an interesting data set, apply something that you learned in the class so far to it, and that's the idea. The idea is to do a little bit of research on this. So in the proposals, I want to see a couple of papers that you're going to read and study, maybe implement. But that's the idea. There's no presentations. There's some question about presentations. There's no presentations on this. This is just do the work as a team, turn in a PDF, summarize the results, and then like whatever code, notebooks, whatever you do it in, have that as well. Okay, it's worth the same amount of all the rest of the homework, so it should be like a pretty easy, like 20 out of 20. Kind of boost that grade in case some of the other homeworks haven't gone so well. Make sense? All right. Any other questions before we get rolling today? Okay, so last week, Chris got you started on recurrent neural networks. Let's see. Nope. Recurrent neural networks. So he used a set of slides from another course that's taught here. So those look really great. Hopefully you got the basics of recurrent neural networks, the idea, right? What we're trying to do there with recurrent neural networks. So like with convolutional neural networks, this is all about coming up with architectures that learn something about spatial relationships and statistics. And with recurrent neural networks, we're trying to learn temporal relationships and statistics. So hopefully you saw that you got through some of the plain vanilla type ideas there, some of the issues with them, like exploding gradients or vanishing gradients, and then some of the attempts at overcoming those, like the LSTM, long short-term memory networks, or those units, medium-term networks. So I see a lot of nodding heads, so yeah, that's good. So we're in a good place. So as we're coming here on the end of the semester, I've been kind of debating what to do next. And so what we have for the next little bit is I want to do concentrate on a use of recurrent neural networks in machine translation. So there's been like a huge amount of success doing translating from one language to another using neural networks. And I want to go through some of the mechanics of that, starting kind of from early attempts at this that were fairly successful, and then building this up to more sophisticated networks, and eventually to get to like the most sophisticated networks, or like the state-of-the-art networks here, things called transformers, in particular BERT, which is like a way of putting together transformers to get really the top translation. It's interesting that so we're gonna do a lot this week with recurrent neural networks in machine translation, but when we get to like transformers actually are not recurrent neural networks. They're actually attention-based networks, and so through the next couple lectures, we'll introduce attention, what attention is in neural networks, and then kind of see how attention is used to do to also do this, to do machine translation and other types of tasks that recurrent networks are also good at. All right, so that's kind of laying out the landscape where we're going to go next. Okay, so neural machine translation part 1. So there's roughly 7 billion people on the earth, and there's roughly 7,000 languages. So being able to translate between them is obviously a super useful thing. And this is some graphic kind of showing the distribution of number of users in the millions, or number of people in the world in the millions speaking these different languages. And platforms like the internet actually provide this like really interesting opportunity to try to do a lot of translation, because it's not really necessarily like speech to speech, like two people speaking together where they need translation, but it's text that needs translation. Although a lot of the techniques we're going to talk about, while they'll be focused on text, you can totally apply them to audio signal as well, but we're mainly going to focus on text, mainly because a lot of these things were developed for being able to do these things with text, in particular because of being used on the internet. So this is sort of, I don't know, this is I just sort of jammed this in because I just like this picture. It kind of tells you a little bit about where we're going. So I saw this tweet once, and I just thought it was like really funny. So this guy's got this picture here of like 4 different kinds of candies from that are not U.S. candies. They're foreign candies, and you can see, these always seem like the output of a slightly undertrained neural net, right? So this is like learning to generate candy names, but you get things like musk sticks, pineapple ones. Now, obviously, these were generated with neural networks, but just kind of, this is where we're going. We're going to be using networks to do, translations. If they're slightly undertrained, you might get funny sounding candies. Dairy milk. I never really thought. I've seen these a million times, but I never really thought about it. It's just like redundant, right? Like dairy milk. Yeah. Anyways, okay. So let's kind of set the stage here a bit. So translation is an interesting thing because language. So not getting too philosophical, but just kind of treading a little bit into philosophy here. Language is really an interesting thing because it's this way that we like outwardly communicate something inward, something that we're thinking, something that we're believing, something that that has some sort of mental life. But when we try to take what's in our head and then put that into language, there's obviously already a number of ways in which you could sort of communicate the same idea with language. So the idea of being able to kind of decide how good a translation is a bit problematic, because there's already a problem, there's already this sort of encoding problem of like encoding what it is you intended in the original sentence already. There's already like a bit of a translation there from like what like your mental state to like how you describe that. And this is going to show up in the ways that we sort of evaluate how good a translation is. And this is very much like when we evaluate generative models of like faces by like looking at the pictures themselves and saying, wow, that looks like a face, right? Like we know when there's been a good translation because like there's like something that we kind of understand about the language and like and like especially when we put like kind of two translations side by side of something, and we can kind of see that like one seems to capture another better. Sometimes we can't tell, but there's always this like kind of human element involved in evaluating like how good a translation is. And you'll see this, like the main score that's used to do these is called a BLEU score, BLEU, and it's basically just like for any translation. So for any sentence that needs to be translated, there's like one or more already human translations available, and you basically are like scoring like how well you're overlapping with those existing translations. So again, there's not like this like ultimate objective score here that you can have for a translation because there's sort of a group of possible translations that will all be about equal, and we're going to kind of see that here. But anyways, the point is like we're going to kind of talk about translation, some of the things that happen in translations and things that we want to overcome. So so what we're going to see here is there's some French phrase that's being translated here. So up here you see the translation that was done by Google Translate at some point in the past. So something in French, and it says, however, within the discipline of machine learning, develop specificity that of deep learning. That doesn't quite sound right? So the sentence that should have been translated from French and English should have sounded something like this. Nevertheless, within the discipline of machine learning, a specialization called deep learning has been developed. So like this would have been, a faithful translation of the French sentence. This is what we got out of some attempt in an earlier version of Google Translate. And when we read it, we already kind of stumble over ourselves because it's grammatically incorrect, right? However, within the discipline of machine learning, develop specificity that of deep learning. That's actually not a proper English sentence. We want to have translation systems that produce grammatically correct sentences at the least, right? Even if they don't get their translation right, we at least want them to like obey rules of grammar and things like that. So this is going to be like one thing that we're going to think about as we think about translation. So like this, another phrase is being translated here. So whatever was in French, it should have been translated as something like, its distinguishing feature is that it is inspired by neurobiology. This somehow got translated to, its peculiarity is to be inspired by neurobiology. So fairly close, but distinguishing feature, whatever the French word was, it got translated here as peculiarity, but it might have made more sense to have called it something like distinguishing feature. Peculiarity has this kind of like, I don't know, maybe it's not pejorative, but it's kind of this feeling of like, there's something wrong with it if it's peculiar, rather than kind of being distinguishing. That's like a little more like a positive way of talking about this. So we're going to always have this issue of, as we go from language to language, to be able to kind of capture the underlying meaning of what the author is trying to say in the words that we produce. Here's another. So like whatever the French sentence was, we would have hoped to translate it like, deep learning deals with computational elements which allow a network of artificial neurons to learn a model of the human brain. And instead we got, deep learning aims to find IT elements, allows a neural network to learn about the human brain model. Like, that just doesn't, it's just like a bad sentence, right? It doesn't, it's not even structured. So, these are all the kinds of things we hope to overcome with in our better and ever developing machine translation systems. Yeah, there's the full translations, and yeah, they're quite different. Okay, so just kind of a brief history lesson. So up until maybe like let's see, maybe like 4 years ago, I think is what we're thinking about. Most machine translation systems would have been something like this, something that would have been in the realm of what's known as statistical machine translation. So this would have had like a ton of components. So a model for the language itself. So something so this would often look like a parser for the language, so like a grammatical parser, something that could take the sentence, kind of assign each word to a like part of speech. How it's some ideas of how they related to how the different words related to each other in the sentence, and then there would be, so you have that for like the two different languages that you were trying to translate into, and then you have some sort of translation model that sort of understood the relationships between the two different languages and tried to statistically kind of map one to the other. And so you often had just like many components that were that existed sort of independent of each other. They weren't necessarily like an end-to-end solution. You just would have different pieces that kind of fit together, and you try to make the best of them, translating from source to target language. So these would often be what we would call context-independent translations. Like you'd just be doing a local translation, not really a translation sort of in the context of whatever the article it is you're translating. So like long-term dependencies between words in the document would be sort of lost in systems like this because you're concentrated on such local aspects of the language, like parts of speech in a sentence, independent models, and while there might be some machine learning in here, it's all kind of done independent, not end to end. Like we hope we can do like what we've seen many times done now in the convolutional network setting with images, where like when we were doing object detection, and we were able to kind of create this whole end-to-end system for proposing regions where objects were, and then classifying those, and then so instead of just having independent systems like that, where eventually what was developed was a full end-to-end system like that. So that's what we're kind of going for here. So this was where we are about 5 years ago, which isn't that long ago, but technologically it's a long time ago. And this is a lot of what these things would look like, right? So it's like you take these sentences, you break them up into parts of speech. You'd have for each of these parts independently, you'd do a translation, and then these language models would kind of know that, like, hey, in English, adjectives go before nouns, but in French, adjectives go after nouns, and so you'd already tagged the part of speech, you already done the translation, and then you sort of do that mapping between the two, and hope that you got a model that like made sense. And sometimes it does, like in this very simple phrase, you actually get a perfect translation, as far as I understand French. But doing this on a large scale will give you like a lot of inconsistencies. So
young means small.
What's that?
Young means small.
Means small? Okay. So not necessarily cute.
No.
But you have petite in French, which is small. And I think this mignon might be cute, but hey, I'm not a French speaker, so. Yeah. And you're,
not even I am.
And you're Italian speaking, so yeah. Anybody want to comment on the French here? Anybody's a French speaker? Yeah.
I think it's cute, yeah.
Okay. So there you go. Okay, great. So this is kind of the flavor of how this worked. All right. So some progress was made in making these kinds of things more complex, and the idea was that you would start to have models that were conditioned on particular words within the sentence. So like there'd be a model that would kind of tell you like what was some of the really important words within the sentence that would help in like anchoring the full translation and then doing the translation, and that helped you to say like turn something about like the bank, where this is not this is one of those classic examples in machine translation where like word bank can be the bank where we put our money, or it can be some part of a river system, right? So being able to like kind of understand that is important. So some work was done. This starts to get a little more complex, but this wasn't necessarily all the systems that are now kind of state of the art. So let's get to those. So what we really want to do here is to get to machine translation systems that are based on neural networks that are going to be, there's going to be recurrent neural networks here because obviously there is a sequential structure to language, like in English, in many, romantic languages, we're reading from left to right, or in other languages you read from right to left, but there's at least some way in which you understand, you process the symbols. So we're definitely going to be using those kinds of models. We have sequences so like the source phrase or the source sentence or the source document, is a full sequence in one language, and we want to translate that to the full sequence in the other. So instead of having like local translations, what we want to do is to get to more global translations that try to do this all at once, rather than just like one bit at a time and kind of try to put the pieces back together. And of course, what we always kind of push for in machine learning is we want these things to be end-to-end. So we want to, end-to-end here always means like we want to like start with a data set, and then like we want to train a model from that data set that does the whole thing for us. So in this case, this would be translate that full phrase, I'm a student, to that full phrase, je suis étudiant, which our French speaker could comment on my pronunciation, but something like that. And we don't want there to be like multiple pieces necessarily. Although it turns out like state of the art often does have like multiple pieces, or at least what usually happens is you have an end-to-end model, and then there's like someone figures out a way to kind of take the end-to-end model and like tweak a piece so that now there's like something that's now no longer end-to-end, and then somebody figures out how to like jam it back in and make it end-to-end again. We'll see some of that as we go through the history here. And I say history, it's funny, like it's 5 years old, right? So it's not that long ago. But anyways, we're going to be looking at the work from a couple of papers from 2014. In particular, they gave us what's known as the seek-to-seek model. Did you guys talk about seek-to-seek when Fritz was? I don't think I saw that in the slides that he did use. So okay, we're going to go through seek-to-seek now. All right, so this is what you learned about last time. Just the basics of recurrent neural networks. Typically, what you've got in a recurrent neural network is you've got some encoder that takes your symbol. In this case, we're using words. This could also be at the like character level, but there's some alphabet determining what your symbol set is, and there's some encoder that turns that into some vector representation. And then in recurrent neural networks, you have this additional aspect where this like the hidden state in this model gets moved forward in the sequence of, or like in the direction of the sequence, and that the state accumulates. So we have some representation of I, and then the hidden state that represents I gets combined with the new hidden state that represents M, and we get a new hidden state that's like the combination of those two, and then that happens again where that hidden state representing the combination of the two gets combined with another symbol, its encoding, and so forth. And there's just like basic neural network stuff happening here, right? So linear operations followed by some nonlinearities, and those get combined together in wacky and wild ways, like in LSTM, where there's like lots of gates kind of turning on and turning off different units and things like that. But the basics are, you're just basically building up the state of the internal state of this network through the sequence of inputs. So yeah, so that's what you learned about last week. So it typically look like the following: inputs are X. There's some weight matrix associated with that. Hidden state is usually with an H. There's some weight matrix associated with that. there's lots of ways to do this, but you typically just see that you do your basic combinations, like linear combination of these. So you do your matrix spectrum multiplications and add those together, apply your nonlinearity, sigma, and then you get the new hidden state, and that gets pushed forward. Yeah.
Is it fair to think about this as kind of like a convolution net, but for words? Since it's kind of
No, because you can actually apply convolutions to sequences like this, but you sort of lose the temporal aspect of the sequence, right? So when you apply a convolution of this, you might, again, like you could have encodings for all of these things, and that would give you, some, maybe think of it as a matrix, like there's like a matrix where like the first column represents the I and the M and the A and the student, whatever. And then you could apply a convolution to that, but so now what you have are spatial filters on that matrix, and that's now like considering more like the kind of the spatial arrangement of those words, which you could kind of argue has like a temporal aspect, but it's not the same thing as like accumulating in the direction of the sequence, like the state as you add new inputs, right? So it's actually, like the mechanics are actually quite different. Yeah. Yeah. So like, again, like one of the main ways it's different is for a convolutional network, this whole thing would be the input, right? Like some representation of this whole thing would be the input, and you'd operate on that. In recurrent neural networks, you build up a state over the sequence of the input. Now, of course, these could be images, and like this could be a video, right? So like this could be, frame 1, frame 2, frame 3, frame 4, and you could do this, and this is how you actually do, you learn on videos, is you combine convolutional encoders with the recurrent idea. But they're different. Yeah. Right, so let's see, what am I trying to say here? This is just more of the same. So the way that you think about depth in these networks is that, so like there's like this layer of a hidden state, but that could also, so while that could be input to the next, for calculating the next hidden state as you add more of the sequence input, there's also, you can have another layer of these things where this vector now becomes input into a, so just like this was input to this part of the state, you can actually think of this now as input and pass it up to another part of the state where there's like another layer of like aggregation or accumulation of the state. And you can have as many of these stacked up as you'd like. This is how you get depth in recurrent neural networks, is in this way. And I think you probably talked about this, but it's always good to think about this as like, there's sort of like a single unit here where like all the operations are the same, and it's being kind of like unrolled in like different directions. And so like each one of these units kind of does the same thing, but like where it's placed in the recurrent neural network kind of determines like the level of abstraction that's being represented at that state, at that part of the network. And like with most machine learning algorithms, like what we are trying to do is we think about these things probabilistically. What we're trying to do is so we have some sort of source, like you might think of it as like, the source being this word, and then what's the likelihood of producing this one here? Or you might think of the source as being this entire sentence and the likelihood of producing this entire sentence here. There's different ways of setting this up, but we typically think of it as like probabilistic. So there's going to be, there's like some like known vocabulary that we're working with, and we're basically like trying to learn things like, given some symbol in the vocabulary, what's the probability that this other symbol in the vocabulary will come after it? Okay, so just like we have encoders and decoders in like thinking about auto-encoding, you have kind of a similar idea here where there's a recurrent neural network. This is getting towards like the seek-to-seek ideas. There's a recurrent neural network that's encoding our source phrase here that we're trying to translate. And so that's just the RNN that takes as input that whole sentence. And then what's typically done is that you have some sort of additional symbol, called boundary marker or an end symbol or stop symbol. And once you get to that, then this sort of marks the beginning of another recurrent network that is your decoder. And its job is to produce the translation, which is again a sequence. So this will be produced symbol by symbol here. And the point is, like, you just know how to do that because there's some symbol that represents when you end the encoder and begin the decoder. Yeah. And then we have a final stop symbol for when we're done. So like this is like just kind of high level what we're doing when we're using recurrent networks for machine translation. So there's lots of ways to think about what to do with these symbols here. You could, if you have a kind of limited vocabulary, you could think of these as like what are those one-hot encodings, right? So like if your vocabulary has, I don't know, like 1,000 words in it, 1,000 symbols in it, you might think of these as like vectors that are of length 1,000, and then the first entry represents the symbol I, the second entry represents the symbol M, and so forth. And so there's a one-to-one mapping between the symbols in your vocabulary and vectors of this kind. Typically, though, vocabularies are much larger than that, and even a one-hot on the 1,000 is already kind of like a bit of a wasted way of representing that kind of information. So there are lots of ways these days of learning to like densely embed symbols like this into a vector space of a smaller dimension, maybe a couple hundred dimensions, and that are meaningful somehow. So there's techniques like word-to-vec or different variants on word-to-vec that are basically just ways of like embedding each of your symbols into a vector, and then those would be used as the inputs, so that we're always working with vectors in our neural networks. And you'd have one of these for each of your languages. You'd have one of these for English, you'd have one of these for French, or whatever other language you're working with. And again, it's just like some way of like efficiently representing the symbols in the vocabulary. Okay, so let's see. Yep, these things all need to be like initialized, and because these things are like all one unit that expects some input. This unit's going to have something kind of coming into it because these units have things coming into it. But often you just start with vectors that are like simply initialized, like they're all set to 0. These are all just kind of like the basic mechanics. You could set them really to anything, but it makes sense to set them to 0 in a lot of ways. And then your forward pass just looks like something like following these arrows. Like you might do this first layer first, and then once you have all those vectors worked out, then you can work on the second layer, and so forth. And then once you have all those worked out, then you can start going through the decoder layers. So this is like what your forward pass would look like. And in your homework for homework 4, you're going to be able to do this. You have to start already. Now you know what to look forward to writing code around doing these forward and backward passes in recurrent networks. Right. So you learned about plain vanilla RNNs. There's some problems there, whether they're exploding or vanishing gradient problems. And you learned about LSTM as one particular architecture for that, or the GRU gated recurrent unit as another. There are others as well, but these are kind of like the main ones that you'll see. And yeah. So okay, so this is how we use recurrent networks to do to learn to map one sequence to another. How do we actually train these things? So we talked about the forward pass. So to do the backward pass, we actually need a loss function to optimize. So so what we are going to do here is we're going to maximize some representation of the probability distribution for this conditional probability. So given the source, so like given where we are, you know, this representation, for instance, right here, what's the probability of producing the representation for the correct symbol here, which would be je in this this network. By the way, I think I have some slides on it now or later, but I want to say it now. One of the great things about recurrent neural networks and using things like this stop symbol is notice that this is a sequence of 4 symbols in English, but we're trying to translate to a sequence of 3 symbols. So like with neural networks, but with computational graphs generally, you really just can't have like a variable number of, say, like states here to keep track of. You need to have that be fixed so that your computation graph can be computed, like so you can work your way through the computation graph and like it all makes sense. And so what you typically have is like you have enough states here to learn like your longest sequence in the in your corpus, like in what you're trying to learn on, for both the source sentences and the target sentences. And then you just use these symbols to say that you stopped, so that you ignore the rest of the computation after that, which is nice. Like you can start your, like, you know where to start backpropagation and those kinds of things. Okay, so how do we do this? So we basically just do what we've done along. We want to maximize that probability. So we just make sure that the thing coming out of our like the outputs from these units are something between 0 and 1, that are giving us an actual probability, and then we're just trying to maximize that. So typically we'll change this into like a negative log likelihood, and like if in this case we want to minimize that, the negative log likelihood. But so we'll have one of those, like we'll have some term in our loss for that particular symbol. We'll have another term in our loss for the next symbol, and so forth. And then we just take all of those and sum them up, and that will be our loss. That will be the contribution of our loss from this sample of data, for this pair that should be translated. And then we'll have, so for each pair, source and target, we'll have that, you know, like that sum over the target symbols, and we'll take an average of those for the batch, and that's what we'll optimize. So we'll do a gradient descent with those. Does that make sense? Oh yeah, we also have, sorry, I should have kept going with that, but we also have the likelihood for that particular symbol as well, because we want to be able to produce that at some point, right? Like that's the way the neural network tells us, like, we've made this translation's done. As soon as you see that symbol, this one's done. Don't pay attention to what's coming next in the network. Does that make sense? Questions? I've been doing a lot of talking here. No one's been asking questions. Yeah.
Actually, I have just about 2 questions. One is, how do you know the French word? Is it like no label you already?
Yeah. So this is like any other labeled data. Like somebody who knows what they're doing gives this to us, right? So someone who speaks English and French gives us this translation. And like in this simple, like for such a simple phrase, I don't think there's like no ambiguity in how to translate it. For more complex phrases or longer phrases, there is some ambiguity, and so you might have multiple targets. So you could have like the same source and multiple targets, or maybe multiple sources and the same target. But you would just train all of those because they're all kind of, they're all teaching the network to produce something that makes sense. Some kind of translation that makes sense. Does that make sense? So like all labeled data. So this is a supervised problem. Like all supervised problems, you need to have good labeled data. And in this case, somebody who speaks these two languages really well provides this to us. Or some other great way of doing this, which I don't know. Yeah, like obviously there's been a lot of translation going on between lots of different languages for many, many years. You can go through, books that have been translated, over the centuries from one another, and you get large corpuses of data, and someone needs to go through and parse them all and align them all. Yeah.
Do we have to be thoughtful where we put that stop? Or in this case, we just put it.
I mean, it's usually pretty obvious where it should be, right? It's like this, it's just like you get this pair, you get this sequence and this sequence. So every single sequence ends with this thing. So it's like so you don't have to be thoughtful. You just have to make sure it's there so that the network knows when to make its transition and when to end.
So if that stop doesn't represent like we're losing, I don't speak French, so I don't know what we're losing here. Like maybe we're losing A or am or something, right? So we don't have to be like, oh, this.
No, we're not losing any. We're not losing anything. We've encoded each one of these symbols, and then we're decoding to each of these symbols. We're not losing anything. This is just saying like, hey, I'm done. Like this sentence is done. So I might have 100 units here. Usually not that many. I might have 20 units here, so I can encode a sentence with 20 words in it. But it might be 4. And so I need to know. I don't have it drawn here. But I need to know when to ignore the rest of the stuff, and then move on to the decoder. And then I need to know when the decoder should be done as well, and ignore what's going on afterwards.
Oh, so it's not we have 4 things and we need 4 outputs. That's not.
No, we don't need 4 outputs. This could be a variable length output. It doesn't need to be 4. It just needs to be like, hey, this sequence is stopped. I'm done. Like this is done. This could have been 10, and it could have translated to 3. I don't know. I can't think of an example like that, but it could have been that way. And so it just needs to know that like there was 10. So this says, hey, there were 4 symbols here, and that one up there says, hey, there were just 3 symbols here.
So we still have. So if that was the example from 10 going to 3, we still have 10 and 10 with.
No, you'd have 10 and 3. You'd have 10 here, a stop, and 3 here and a stop. Yep. It's just a way of letting you know that it's done. And you
period.
Yeah, like putting the period on it in some sense, yeah. And yeah, that's right. So you have to have that again because you want to deal with this variable length problem. And so this is the way you deal with it. You have a symbol that says I'm done. And if you don't get that symbol, then you just keep working away. So it's kind of unfortunate that there's like 4 blues and 4 reds because it makes it look like it needs to be balanced, but I'm just trying to indicate that it doesn't need to be that way. It could have been 10. It's usually you set up with like there's 20 and 20, and then the stops tell you when to transition or stop. Yeah.
So I'm just wondering, when it's computing the loss, does it backpropagate through each one of those 4, and it just backpropagates the loss values?
So this one will backpropagate through, right? So if you follow these arrows back, it's going to backpropagate through that and through that and through that and through that. If you wanted to know something about the input, but like from here, the computational graph moves in that direction. So there is no backpropagation forward in time. It's always backwards in time. Right? It's like so like when I'm backpropagating through the negative log and probability of etudiant, the backpropagation works through here and it doesn't go through this part of the graph.
Okay. So is the loss just computed once for that final cell, or is it computed for all 4 of those cells and then those all send?
Oh yeah, so there's one like negative log likelihood term for each one of these cells here. Then you sum those up, and that's the total loss for this sample, for this pair, right? And so now your mini-batch might have 32 or 64 or 128 or some awesome powers, 2 of those.
So does that just go to?
And then that would be the average of all those sums.
So does the backpropagation start on the last cell then? Is that where
Well,
it starts?
No, I think so. Just think of it this way: so the total loss that you're like for a mini batch is just like the sum of a whole bunch of these negative likelihoods. And so each one is going to be treated, treated the way that it needs to be. So like if this is like the stop symbol here, the backpropagation will start here, but just for that contribution to the loss, right? And then you have this other contribution to the loss, and then those two terms will come together here, right? Because like they're part of this, they're all part of the same graph, and then that will be combined with like the next, like the gradient kind of coming through here, and then combined with the gradient coming through here. Then there's this full gradient for that, for that phrase that's coming through that whole thing.
Okay.
So
That's what I thought. I was just.
okay, right, cool. Is there other questions? Yeah.
So how do you calculate the probability P? Is it a function of the hidden state of the layer 2? Or how?
Yep, exactly. So like what you'd have, and even though I said never use sigmoids, you actually see a lot of sigmoids in recurrent network. So you'd have some, so like this is going to be a vector. So now we have a set of weights that we do a dot product with that vector. That's going to give us a single value. And that's going to be input to our sigmoid. That's just going to give us a value between 0 and 1. So this is giving us a probability. And then we apply the negative log to that. And that's the thing that we're optimizing. So it's very similar to what we did with like binary cross entropy. This can be like this can also be So you can see sigmoids here. You can also have cross entropy here for the entire vocabulary as well. That's also a thing that you can do. Although that can be difficult. So sometimes you just see like the multi-class multiple sigmoids, but you can also you have some way of measuring how good this probability is compared to the correct probability. Okay, other questions? Okay, so yeah, here's our backpropagation slides. So yeah, I should have gone to these to answer your question, but you just followed all the arrows backwards through this whole thing, and those gradients get accumulated all the way back. So lots to keep track of with RNNs. But there's always lots to keep track of. It's the same thing, right? Like once you unroll it, it's just like exactly the same thing. There's like a forward way through the network, and then a reverse way. All the arrows backwards. Okay, so you probably already seen this, but just kind of pointed out. When we're training, obviously we know, like we're given the pairs, the source and the target, and so we train with those. But at test time, we don't know what the correct translation is, right? So what we do is we use this this network to produce probabilities across our entire vocabulary, and then use those probabilities to decide which symbol we ought to use. And so and then whatever symbol we chose to use, that becomes input into the next to choose the next word. So this is kind of weird, right? Because errors can build up really rapidly here because of this dependence, the sequential dependence. So here's what I'm saying. So so you have this sentence. So this is at test time. Here's your input. I am a student. Stop. So you've got all this state built up, and now you need to make a prediction for what ought to come next. So now this thing predicts probabilities for all of the so if we use softmax here over a small vocabulary, we would get something like this. So this is like all the words in our vocabulary. We have étudiant, suis, the stop symbol, and we also added this other word, moi, just to kind of show you where things could go wrong. For some reason, it thinks that this should be moi instead of je, because it's assigned a high probability there. So we would pick moi, and then that would go into that would be input into the next state here in the decoder. And so that's combined with all of this state here, just just like in a forward pass way. That again gives us a probability distribution on our vocabulary. We here pick the SWE because it's got a high probability. That becomes input to the next one. We pick it to the on. That's because it's got the high probability assigned to it. And then hopefully we get a stop symbol as the thing we ought to pick. So again, this is a little bit different again from like convolutional networks because if we make an error somewhere in this, that error can start to build up, and like the error can be correlated as we move forward in time. We can start getting worse and worse translations. So it's just kind of a thing in these that can be hard to overcome. Yeah.
Can you do a state where you're basically just never getting a stop signal? Or you're just
Well, you would eventually get to the end of, like, you'd only have so many of these units,
Okay.
right? And then you just get to the end, and then you'd be done. But yeah, like theoretically, you could have an infinite number of states and then not, never stop. That would be a really bad network. You'd want to keep training.
toddler network.
You'd want to keep
Keeps
training.
on talking, every time it makes sense.
Yeah.
Well, isn't it only one cell that's unrolled? So this, like by nature, RNNs can go forever, right? Like all RNNs, because it is one cell. You just unrolled it.
Yeah, you could have it go on forever. If what you're saying is like they're sharing weights in each of these cells, yeah, like that's you could have shared weights, but you don't. So that would be like a single cell being enrolled, but you don't have to have shared weights. You could have each one of these could have its own weights, and you'd stop. But it could go on forever, but you typically don't have it go on forever because, like especially with static computation graphs, like the static computation graph can't encode this goes on forever. It has to literally be unrolled so that it knows like where the beginning is and where the end is.
So are most RNNs static or dynamic cells?
What do you mean by this? Like you mean because when I apply static, I apply that to the computation graph.
Well, so I'm saying static as in let's just say there's 20 decoder cells versus I've seen that many times. It's just you have one encoder cell, one decoder cell, and that keeps getting reused.
Yeah, so you're talking about the shared weights.
Yeah.
Yeah. So I think you typically share weights is like the typical thing to do. Yeah. But whether or not you share the weights, especially in a static graph, like you have to know how many, you have to know all the dimensions,
Just
including
do batch operations.
just because the computation has to know, like the graph itself has to know what all its nodes are up front. And so even if you are sharing weights, like it has to know that like this is this is node 1, 2, 3, 4, 5, 6, and 7. Like it has to know when that stops. And when you're using dynamic graphs, then you can get around this. So you could get into a situation where like maybe it never stops producing, or never produces a stop symbol, so you just keep producing. But you'd also want to you'd obviously be smart about that and stop it. Yeah, and it turns out that a lot of kind of sequential stuff like this is done with dynamic graphs. Like there's definitely like a preference for like PyTorch over TensorFlow for these kinds of things, especially as they get more complicated than this. Like where the unrolling is like conditional on like certain states in the network. Good questions. Other things about this? Good questions? Okay. Yeah, we just do simple maximum likelihood. So this is just a comparison of, let's see, this is weird. Yeah, okay. Yeah, so this was the state of the art in 2014 with the SMTs. This was the Statistical Machine Translation. So this is some measure of how much our translations overlap with the existing human translations in the test set. So like 100 would be like perfect overlap with all the possible translations. It's never like that. Like good scores are like now pushing into the 40s here. But so like this was the state of the art, and then this is what these models produced in 2014. So you had just a straight sequence to sequence, what we just saw. This got a score of 34.8 compared to like, the state of the art 37 statistical machine translation. And then if you kind of combine these two, which I don't actually know the details of how these are combined. Can't remember like what that was exactly, but you got a little more out of it, probably using the parsers and things like that. But you got a little more out of it. So it didn't beat state of the art in 2014, but it got really close. And like the point that's trying to be made here is that like you had decades of research to get to here, and only 1 to 2 years of research with recurrent networks, you got to something really comparable. And of course, it was trained all the way to the end. Did you have a question? Okay.
What does blue mean?
Yeah. So this is the score that's used to evaluate how good a machine translation system is. And so basically, it works like this: you have a test set where you have a source phrase, and then one or more possible translations. Usually, there's more than one. And then you take the translation that comes out of your network, and you do a kind of like overlap of those two translations. So you're looking for overlaps in the words produced and in the order in which they're produced. And so like 100 on this blue scale would be perfect overlap for all of the examples in the test set. And so something like in the 30s is something like, like a 33% overlap. Overlap's kind of a loose word here. It's actually kind of a complicated measure, but like 33% overlap on average with the translations. The real point here to try to get from this is that like this is where, given this measure, this is where state of the art statistical machine translation was, and this is where neural machine translation got to. So like they're fairly comparable. As we go through the next couple of lectures, what we're going to see is that these numbers start creeping up into the 40s, and they far surpass what's happening on the statistical machine learning side. So no one's really doing any of this stuff anymore. They're using the neural networks to do this. Yeah. Other questions about that? Okay, so the work that we've just been looking at, those units, those rectangles in each one of those, in each one of the, each one of those rectangles there you could use any kind of recurrent cell there. In the work done in the paper, the actual seek-to-seek paper, they used LSTMs, and I think they used 4 layers in those LSTMs. Is what it is. And then you can of course change out the encoder and decoders. So a couple other papers did this with the gated recurrent unit. So it's like an LSTM, just a little bit simpler. Kind of performs the same. And then earlier than this, people had done it with like with CNNs, not recurrent networks, for the encoder, and then some kind of decoder, like an upsampling kind of thing for the CNNs. But yeah. So the point is like you could like that. So like seek to seek, like technically uses LSTMs as those cells, but you could replace those with anything and still kind of have the same like computational path. Okay. Right. So what's next? So now we get into more advanced neural machine translation. But before we do, actually, I think we're going to end a little bit early today. Before we do, I want to show you these attempts at doing machine translation. Does anybody speak or read any of the languages that are actually up here?
Chinese, the bottom down, bottom right.
This one right here? Okay, so how would you translate this sentence? Or this, it's not really a sentence, right? Like, how would you translate this product?
That seems like a name. That's a name. Actually, this is the first time I heard this name.
Okay, so somehow this got translated to meat, muscle, stupid bean sprouts. What's the stupid in this?
This is the sixth word.
1, 2, 3, 4, 5, 6. This one right here.
Yes.
This actually is stupid.
Yes.
Somebody else is saying yeah. So why would there be why would that symbol show up for this product, for this food? Okay, while you look at that. So yeah. So clearly this is not, even if this seems appetizing for Chinese people, this is not appetizing for like English speaking people. Because like stupid is not usually how you describe appetizing food, right? So like there's a big miss there. These are really comical, right? So so what language do we have up there? Another Chinese translation? Oh, Japanese. So anybody read Japanese here? No? So apparently it's instructions to tell you where to go to find the bathrooms from where you are reading this sign, right? So this says, for restrooms, go back toward your behind. Which, obviously, like when you read it, you're like, oh, I get what they're saying. It's like go backwards, right? But like there's like this really literal translation here. And the unfortunate use of the word your, the possessive your, and then followed by behind, while talking about restrooms, like this doesn't make sense, right? Yeah, I don't know. Not sure what language that is, but yeah, some kind of Arabic language. But I don't know if it's straight into Arabic or some other kind of something related to it. But sale of chicken burger. So it probably has something to do with just like these are chickens that you can go buy that have been killed or just get the meat from it or something. But somehow this gets translated as sale of chicken burger, and I think this one is maybe the most comical. This looks like some kind of like Scandinavian language or whatever, but it's getting translated to baby. So this is baby walk, baby noodle, and obviously our favorite deep fried baby. Now the baby here, is referring to some sort of like state in which the food is in. Like it's early, tender, kind of picked, whatever.
Well, I was thinking because it says kids menu.
What's that?
It says kids menu, so I was thinking maybe.
Oh yeah, maybe it's referring to it's a small portion or something like that. Yeah, who knows exactly what it is, right? But obviously it's like a huge miss, right? Because it's like while it might be like a fairly faithful translation of these things, it's like once it gets into this other language, these words are just totally inappropriate choices. You need some other choice. This is what makes machine translation hard. And how do you know these things? Well, when you're just doing like these really kind of small localized translations, like it's really difficult. But as you like see a language in like a much broader context, like larger documents where like much longer term relationships exist between the meanings of words and the context in which they're used, then you start to get more at like the semantics of language rather than just like the grammatical, rules of language. And so next time we'll go into some new ideas of machine translation built on what we were just doing. That will add in they'll add in elements that allow us to get at much longer term relationships. So like LSTMs were developed to allow us to get at much longer term relationships without developing like a long, like an exploding gradient or vanishing gradient problem. So exploding gradient's not that too big of a deal. You just kind of clip the gradients and say you can't get any bigger than this. But if vanishing is a problem because then you have these long-term relationships. If your gradient is vanishing, there's just no signal to tell you how to relate like, this thing at the beginning of a document to this thing at the end of it, or some long sentence. But there are other ways to get at this that are not necessarily recurrent, but that allow you to learn something at these longer, just longer distance relationships within the sequence itself. So we'll do those next time. But I'll just kind of leave you with these web translations. Hoping to get something better than meat, muscle, stupid, bean sprouts. Okay. That's it.
But I was just wondering, so we want to do something like this. We're kind of just wondering, like, how to turn it on it's like filters that you got, like, you have to,
Typically, what you want to do is you want to find like a new job. So like, you could use all the same. You could use all the same. Networks, retrieval networks, and that kind of stuff. But you typically want how to someplace else. Certainly wasn't having kicker. But like, it also kind of more like some super resolution might be a little bit tricky. Also, you can also just take like the library photos, downset, and then try to
I have like a random, maybe pushing it off in the lower aspect ratio and have like a network be able to change it as you fill it out. Sort of.
So like that would be, that's not super resolution, that's more like when it's unpainted, so like you want to wear what's missing. Yeah, so the difference between like super resolution and that super resolution you're going to go from a really lower resolution. So like basically expanding it. This is where when you're painting, you have very information at like near the pixels. You just have it within the areas of the instead of interpolation problem, it's extrapolation. So they're both cool. That's a great idea. But take images, chop them off. You know how to train the model and this is like easy to test, right? You can just do instruction. Right, so you're going to make a prediction about the values of the pixels in the area that you and the way to evaluate that is just to like compare that pixel by pixel with the actual like these people as the vectors in one big L2 difference. It's a great problem. It's perfect. Yeah, that's perfect. Because we can't really do anything around that. Like it's kind of a small step from one to there. So this is a small area. Where like a super resolution might turn out to be really kind of fun. I think like your photos might actually be really funny. But I don't know, like don't do like you can totally retrain these things on internet type data sets, but like but then like adapt them to using data sets. So like maybe more you want to super resolve like usable maps and like there's lots of topic that things you can downside that's like that's got utility, right? You want to be enough people to say, well, it's going to be in this family of things. And obviously, you might go into research and decide just different for me, don't say like, oh, I'm just going to use residents of the side because of this paper. Make sure so much just you have to
Not necessarily.
Okay, cool. Let's go. Yeah. Two classes. We're doing so each time the sequence is like what's the time possible? No, it's great. Right. And then you guys can have your time spending. Right. So these are that's like 72. At the end of this, it's good I guess it just goes but at the end of this, it's like, what I'm going to say, and you're going to use I'm going to software transformation and turn that into, so if you something values is 0 and 1, you're going to train it, you're negative, you're kidding. Zeros and you're red. Like especially for like a single, like this is one. But you can also imagine like taking like if that is a problem, you can take like windows of this and you get like 10 or but you might maybe just take like the average something like that. So you some of the steps then that's your I know. Yeah, like that's what you got. Well, if you take I like once you start yeah, so that would definitely but also you could just that's a great point. Yeah, so, I mean, what you have here is, you have like one dimension. So you really just have this 180 type filter right. So you could just do, you could just do a full
something like that, right?
like you just start with this thing.
So it's not unique.
If you start with this thing, you can just do.
There's like possibility of like, max, like doing some of those, like some of your assets.
And train that.
Or,
If you do that as well, it probably won't do as well as say like. So just do it. This camera does something interesting. It doesn't have to. And like, one nice thing about using like shared weight units is that it's recognize, you know, like, it'll recognize like a peaking like anywhere in the sequence rather than like say like being here, which like something like this is going to learn this here or this here, but not like. Not be set up in such a way that like it can just recognize something. Okay. If what you do is do shared weight, so each of your cells has the same, because then you know what it's doing is that it's like anywhere here it's like okay, so statements like recognizing that
Don't get like close to
1 second that can happen here, or that can happen here later. But this same unit is
it's harder to online here would be
like the whole sample like streaming, right? Like that's not really what it's data copies, right? It's data where you do all these, you do these things in batches, so you get a whole bunch of these in batches. You just train it on, you don't really give it as like a stream. Online learning is something you do where you like when maybe you have too much data and like you need to kind of work like small portions of it, like in real time and like update your network in real time. But like this problem, it would just be really like you could try to explain that, but it'd be really forced on this.
I was just thinking online, so like experiments my day experiments so like we're always going to this, but I guess if you learn this,
yeah, so like, just you know, train it with the data you have, and on Monday you're going to do some experiments, just train it on all that data plus the new ones, and it should get better as long as the data is consistent.